When the last star goes dark, the universe won't end with an explosion. It ends with a long, slow fade. No new light, no new heat, just colder space and older matter. So here's the question that sounds like science fiction, but is actually physics. If the universe runs for long enough, what is the last material still left? Not the last planet, not the last civilization, the last ordinary matter, when everything energetic has already burned out. And to be precise from the start, this story has an if. If a key particle is truly stable, if protons don't decay, then physics predict a kind of end state for normal matter. It drifts toward the lowest energy nuclear configurations we can make through known processes. But if protons do decay, then even the toughest matter eventually dissolves. So this video is not one material survives no matter what. This is, under the most widely discussed long-term scenario for ordinary matter, what persists the longest, and why? And the answer is surprisingly unglamorous. It's not a supermetal. It's not a crystal from another universe. It's the quiet endgame of nuclear stability, matter trending toward iron group nuclei, stored inside the cold remnants of dead stars. That's a material that doesn't win. It's the material the universe settles into. Before we pick a final material, we need to define what the end means. The most common long-term picture in cosmology is a form of heat death/big freeze. The universe keeps expanding. Usable energy becomes harder to concentrate. Stars stop forming. Existing stars burn out. And everything trends toward colder, darker equilibrium. In that scenario, the drama isn't a final event. It's that structure stops happening. Galaxies separate beyond each other's reach. Star formation ends. Remaining stars die. Black holes eventually evaporate on extreme timescales, theoretical via Hawking radiation. And what's left is mostly dark, cold space, long-lived stellar remnant sand matter that can no longer do much work. So the stakes here aren't survival as a victory. It's survival as a physics outcome. What remains isn't what's strongest. It's what's lowest energy and hardest to transform. Which brings us to the engine that decides what lasts at cosmic scales. Nuclear binding energy. Stars are not just light bulbs. They are element factories. A star starts by fusing hydrogen into helium. In bigger stars, fusion continues, building heavier elements. But fusion has a limit. Up to a point, fusing heavier nuclei releases energy. Past a point, fusion costs energy. That turning point sits around the iron group, iron/nickel region. That's why iron shows up in this conversation at all. It's near the end of the road for energy-producing fusion. Once a massive star builds an iron-rich core, fusion can't support it the same way. Collapse and supernova processes follow, depending on the star's mass, leaving behind remnants like white dwarfs for many stars, neutron stars for more massive ones, black holes for the most massive outcomes. Here's the key idea. Even though the universe produces many elements, nuclear physics has a preference. Over vast timescales, if reactions can happen, matter tends to drift toward more stable nuclear configurations. So the last material story begins in stars, because stars decide the initial inventory of nuclei, and remnants decide what can persist for absurdly long times. At the heart of this is the nuclear binding energy curve. Think of it as nature's stability map for atomic nuclei. Some nuclei are easy to break apart. Others are energetically comfortable, lower energy per nucleon, meaning they're more stable against certain transformations. Iron 56 is often cited as a near peak of binding energy per nucleon, with nickel 62 also extremely stable by that metric. The exact most stable depends on how you define it, but the point is consistent. The iron group region represents a deep valley of nuclear stability. That's why fusion up to iron releases energy. Fusion beyond iron generally requires energy input, and the universe's normal fusion engines don't push matter past that point for free. So if the universe gets old enough, and if matter can slowly transform under extreme conditions, the trend is toward iron group nuclei. Not because iron is magical, but because it's energetically favorable. But here's the twist. The final material doesn't appear because stars keep running. It appears because the leftovers keep evolving, slowly, inside stellar graveyards. Most people imagine the end of the universe as emptiness, but the more haunting picture is this: a universe filled with dead objects that persist, not because they're active, but because they're hard to change. White dwarfs, for example, are long-lived stellar remnants supported by electron degeneracy pressure. Over unimaginable time, they cool. In far future scenarios, they become black dwarfs, cold, dark, inert stellar cinders. Not observed today because the universe isn't old enough. This is theoretical future evolution. And inside those remnants, matter is stuck in extreme density and pressure conditions that change what slow means. This is where you encounter ideas like extremely slow nuclear reactions driven by quantum tunneling at high density, processes that could, over absurd timescales, shift compositions toward more stable nuclear states. So the material that survives isn't a shiny substance. It's the end state of ordinary nuclei under the universe's long relaxation toward stability. A cosmos that doesn't end with a bang, but with cold objects whose composition drifts toward iron group stability as everything else fades. Now we need to handle the biggest caveat, honestly. This entire picture depends on whether protons last forever. Here's the hard truth. If proton decay exists, then ordinary matter has an expiration date. Some grand unified theories predict proton decay with enormous half-lives. Numbers like 10 to the power of 34 years or more are commonly discussed in the context of experimental limits and theory. But proton decay has not been observed. What we have are lower bounds from experiments like Super Cameo Candy and future sensitivity goals from projects like Hyper Cameo Candy. So, our story branches. If protons do not decay, ordinary matter can persist extremely long, and the iron group final inventory story makes sense as a long-term attractor. If protons do decay, then even iron group nuclei eventually dissolve, and the last material becomes something more like radiation and extremely low-energy particles rather than atoms. This is an uncertainty as drama. This is uncertainty as real physics. And it changes what survive means. So when you hear the material that survives the end of the universe, the honest version is, if ordinary matter is stable, it trends toward iron group stability and lives inside dead stellar remnants longer than almost anything else. Now, let's make this feel relevant to Future Forge, not just cosmology. Here's why this belongs on a materials channel. Because the universe is doing what engineers do, just at insane scale. It's minimizing energy. It's trapped by barriers. It's governed by kinetics. On Earth, we design materials around energy landscapes all the time. Superalloys that resist creep by stabilizing microstructures, coatings that survive oxidation by forming protective layer ceramics that endure heat because their bonds don't want to rearrange metastable materials that last because transition barriers are huge. Diamond is a classic example. Under ordinary conditions, graphite is more stable, but diamond persists because the conversion barrier is high. That's metastability, stability by kinetics. Cosmic iron stability is similar in spirit. Matter trends toward low-energy states, but the pathway can take absurd time because nuclear transformations require extreme conditions and quantum tunneling. So the lesson isn't iron stars are coming. The lesson is durability is often about energy minima and barriers, and the universe is the most patient materials engineer possible. Let's translate the cosmic idea into real engineering. In turbines and jet engines, superalloys survive because we engineer microstructures that resist diffusion and deformation at high temperature. In spacecraft, thermal protection works by controlling how heat moves, sometimes by sacrificing material, sometimes by insulating, sometimes by radiating. In nuclear energy, materials challenges are defined by radiation damage and long-term stability under bombardment. Again, energy landscapes and defect evolution. All of these fields share the same core question the universe is answering at a cosmic scale. What state does matter relax toward, and how fast can it get there? Materials science is often the art of slowing relaxation, preventing corrosion creep, phase changes crack growth. Cosmology is what happens when you stop preventing it and let time run. And that contrast is powerful. It makes you see durable not as a vibe, but as a physics strategy. There's another extreme uncertainty people bring up: vacuum decay, the idea that our universe could be in a metastable state and transition to a lower energy vacuum. This is highly speculative and not something we can treat like a forecast. It's discussed because particle physics suggests metastability scenarios depending on parameters like the Higgs potential, but translating that into will it happen is beyond what science can answer today. So here's the honest boundary. Proton decay is a measurable target with experiments pushing limits. Vacuum decay is a theoretical possibility with huge uncertainty. Both remind us that ultimate survival claims must be conditional. That's not a weakness of science. It's what responsible science sounds like. So what's the breakthrough here? Not watching iron stars form. We can't. The breakthroughs are in what we can test now. Tighter limits or detection of proton decay, better observation of white dwarf cooling and crystallization signatures better. Constraints on neutron star interiors and dense matter behavior. Improved models linking nuclear physics to long-term stellar evolution. In other words, we're not predicting the end for entertainment. We're using the far future as a microscope on fundamental physics. And every time we tighten those constraints, we understand what stability really means, whether for nuclei, for matter, or for the universe itself. In the next 5 years, expect improved observational and experimental constraints, better surveys of white dwarfs and their cooling behavior, continued proton decay searches more neutron star data from multi-messenger astronomy. In 10 years, next-generation detectors and observatories should sharpen the physics, more precise limits on rare particle processes, stronger constraints on dense matter equations of state. In 20 years, the likely win isn't new material. It's a clearer answer to the question that controls this whole episode. Do protons last forever? Because that single fact decides whether the last material is an iron group end state or whether ordinary matter itself has a time limit. This episode connects directly to Future Forge's core theme. Materials are energy landscapes. Manufacturing is controlling pathways. Durability is managing kinetics. Whether we're talking about a turbine blade, a spacecraft heat shield, or matter in a dead star, the logic is the same, only the timescale changes. If you're watching Future Forge, you're the kind of person who understands this isn't just cosmic poetry. It's the deepest version of material science. What lasts, what decays, and why. And the next time you hear a claim like unbreakable or permanent, you'll know the real question. Permanent under what physics? Under what time scale? Under what pathways? So what is the material that survives the end of the universe? Under the best-known long-term scenario where ordinary matter remains stable, the universe trends toward iron group nuclear stability locked inside the cold remnants of dead stars, matter that persists not because it's heroic, but because it's hard to change. But if proton decay is real, then even that dissolves. That's the beauty of this story. It's not about a fantasy substance. It's about how physics defines lasting. If you want more episodes that connect extreme physics to real engineering, metastability, energy landscapes, quantum effects and materials, subscribe. Because next we can explore the opposite question, not what survives forever, but what fails first, and why engineered materials on Earth can't escape the same laws, only delay them. The future isn't just what we build, it's what we can keep from falling apart.